skills that I presented to you in this morning's lecture. Now, I have another lecture here, but they're otherwise engaged, so this will be a busy one for me, but you just have to bear with me. We'll split you into 3 groups because it's hard to get you in around this machine all as one big group. Okay? But I'll bring you up individually in small groups and let you see. But just to talk about what we spoke about in the lecture. What we must start with is the design process. Now, this is a very simple 3D CAD. Have you used parametric modeling software? Have you used SolidWorks? DCG students have, yeah? Alright, and I'm sure you probably do for design purposes in your Leaving Cert engineering project. No? You should. Okay, so you can see, look, this is a very simple model in that. A very simple extrude of a cylinder, a hollow cylinder, 2 more extrudes of 2 square-based prisms, and then a cut down through the front of this. Okay? The end result being this product here. Now this is a very simple product, but it's good for just to demonstrate what I want to talk about. Okay? So literally the first step in the process, having designed the product in 3D CAD, is to convert it to an STL file. What does STL stand for? Come on, I presented this to you at 9:30 this morning. Stereolithography. Excellent, okay? So stereolithography is a word that you're all going to have to learn how to spell. Alright, because it is going to be asked about in that question. Question 1 being in your Leaving Cert paper, you are going to write the word stereolithography a number of times, okay? And it's basically the 3-dimensional selective printing of an object, alright? The rapid prototyping, the 3D printing, all of those terms that we use to describe rapid prototyping, okay? So, first thing, in SolidWorks, it's incredibly simple. I have a 3D model, I go File, I go Save As, and I change the file format from a part file to an STL file. And that is as simple as it is. Okay? Now, just to show you a little bit more detail what's actually happening here, I'm going to click on the options for this, get this out of the way, so you can see the model at the same time, and I'm going to click Preview. Right? And what that does is, it shows me what's actually happening in the model when I change from a part file to an STL file. And basically what it does is, it triangulates the model. Okay? So it splits the surface of the model up into triangles. Right? Now what do we know about a triangle? At each corner we have how many points? 3. Yeah? Triangle has 3 points, yeah? Okay, so now what the CAD software is able to do is, it's able to tell me the coordinates of each point. So now every point on every triangle, the software knows where it is in space. And that's basically what the conversion from a part file to an STL file does. Yeah? You get that? So that's critically important. Now, this software, this machine over here, is able to interpret this part file. Okay? Now this was a bit simple, so we didn't build this today. So, what we did instead was, we built this. Okay, and that's what's currently being built in the machine. This is the end result. So you can see what it is. It's just the casing of a digital camera. Yeah? So that's exactly what we're rapid prototyping, and you can see we're doing it in 2 halves, so it's actually able to come apart. Okay, there's a little ridge here that we're able to test for fit. Okay, so like when you're asked, what's the purpose of rapid prototyping? Well, it's to create a prototype so that we can test things like fit. So do 2 parts actually fit together? Like form, is the shape right? Does it feel right to hold? And that's something that I can't. Okay, here CAD model is great. 3D CAD model, I can rotate it in space, I can look at the curvature on the features, I can see does it look right, but I can't hold it and actually see what does it actually feel like to hold. Okay, so is the button in the right place with my index finger, for instance? Am I putting either of my fingers at the front in front of the lens? Yeah, things like that. Is the screen suitably sized at the back? Right, so here, okay, we get an indication, but in reality, if I zoom in, zoom out, what's the correct size? Does it look suitable here? We're going to get a suitable sized image on the camera when we take a picture. Alright? So they're the 4 most important things, and if you can remember them, you're going to have a fairly adequate answer for your exam answer, okay? Fit, do parts fit together. Form, is the shape right? Ergonomics, to test how does it actually feel to hold, or to sit on, or to interact with, or, yeah? So how does the human body actually interact with this part? Okay? And finally, aesthetics, how does it look? So, is the curve suitable? Is it too big? We need to minimize that, etc. Alright? So what we did was, you can see this is an STL file over here. So we converted this to an STL file and we bring it over to this machine. I'm going to bring you over in, I'll try to bring you over in 2 groups. So half of you want to come over for a second and try to gather around the machine so you can see in. Yeah, that's perfect. Okay, so just so everyone can see in. So what's currently happening is, the machine is just after actually dragging in a fresh sheet of paper, so it's probably dragging in another one by the time you're finished, okay? So what it's doing now is, that's a little blade over on the left-hand side, see the little silver part? And it's going around cutting the current cross-section that we're working on. So the blade, what length do you think the blade is? A mil? 0.1 of a mil. So the blade is the thickness of the sheet of paper. Each sheet of paper is 0.1 of a mil. So it goes down through that sheet, it goes around and cuts that cross-section, okay? What it's currently doing is, if you look in, it's actually after cutting a load of small squares as well. See that? And that's the waste material. So what it's actually doing is it's cutting the waste material up into small, manageable cubes. So look, this is it. So the end product ends up being a big block of A4 paper with a model consumed inside. Okay? And what I can do is, because it has cut the scrap material into these small cubes, we can actually just peel away that waste material. Okay? See? You can see it's done all that, right? And it's still cutting out the waste material first. And you just wait a second. It's going to change processes now in a second. Now, okay, now what you can see is there's a wheel over on this side toward you. can see the black vending wheel, right? And what that's doing is it's distributing spots of glue. Okay? So now, let me bring you over to the PC and explain that more detail. So there's our STL file after we split up into 166 layers. Okay? So 0.1 of a mil each layer, so the model is 16.6 mil in height. Yeah? Okay, so you can see we're currently just working on layer 63 of 166. So not even halfway there, and there's still 7 hours left. Right? The only thing about rapid prototyping is that it's not that rapid at all. Okay? But if you do think about it, if I produce a CAD model and think that 10 or 12 hours later I can actually hold it in my hand, that is a fairly fast to be able to hold a prototype in your hand. Okay, so if I zoom in, they're all the different layers. Yeah, there's 166 of them down along. So 166 sheets of paper dragged in, 166 different cross sections cut. Yeah, each cross section is glued together. All right. And now, just to look at it in more detail, I'm going to look individually at layer 63. So I click here. I'm going to type in 63. Look at that layer. So now that's what we're currently working on. That's the 63rd sheet of paper. Yeah, so you can see there, first thing it did was it cut out the cross section of the actual camera at this height. Then it cut all the squares for the scrap material. And all the green dots are glued and all the red dots are glued. What do you notice about the green in comparison to the red? Green is straight lines and they're further apart. So the glue is distributed a lot further apart. So that's why it's a lot easier for me to break this off. Yeah? And if you look, let's try split a piece of the scrap material. See those little dots along? See the dots there? So they're the green dots of glue. Right? Because there's so few of them, it's easy to pull apart. Right? Whereas inside in the model there's a hell of a lot more glue. So inside in that there's red dots of glue holding the model apart. And that's why it doesn't pull apart. So the scrap material comes apart very easily, or the waste material comes apart very easily, whereas the model itself stays intact. Okay? So, just to very quickly show you the last one of the limitations of rapid prototyping, because we're using flat sheets of paper, right, and every cut, so imagine when we cut with a vertical blade, the edge of the paper ends up being vertical. Okay, so even though this is a curved surface, it's not really. What I have is a horizontal and then a vertical cut, and then a small horizontal bit and another vertical cut. And the vertical cuts are very close together, so it appears to be curved. But if you look closely at that, and you can pass it around and look at the edge as well, you can see all the layers of paper, but you can see them on the curved surface as well. So if we wanted this to be an actual representation, we're not finished yet. Right? We'd have to get sandpaper and try to sand it. And because this is paper, we'd have to try and spray it with something first to try and solidify it a bit better. Then sand it, and then maybe prime it and spray paint it, etc. Right? So we could go a lot further to try and produce this into an actual prototype that looked like the finished product, right? With finishing processes. Okay, so usually this is only one step of the prototyping process. Okay? So I hope that gives you an idea. Right, if you want to take your seats again, I'll bring up the other group and then we'll have a chat about all the processes now in a second. Okay, the rest of you can come up from here so. Well, we're talking about SLA, which is what? stereolithography. So be careful. An STL file in SolidWorks stands for stereolithography, and it's used for everything. It's used for all the processes. So this is what I was talking about. Stereolithography is sometimes used as a generic part, or as a generic term for rapid prototyping or 3D printing, right? But it's also used for the specific process of, someone explain stereolithography to me. What's the different elements? How would you describe it in comparison to the other processes? Good man. It has a liquid polymer vat full of liquid polymer. We have a machine here. It has a 300mm by 300mm table. So you know the length of a ruler? If you square that, that's the capacity that we can print, right? And to fill the vat, right? So the vat's about that deep, and it's only that by that, costs 40,000 euros. To fill it with the photosensitive polymer fluid. Okay? So you can imagine to produce a part like this costs 2,000 or 3,000 euros. Because you're using up a certain percentage of that vat. Yeah? Okay, so quite expensive, but still deemed to be a very, very cost-effective form of prototyping. Okay? And the reason is, this is a case study, and this is a good case study. This is an SLA part, right? It's a part that a company wanted that they could, so, I don't know if you've ever, I canoe and kayak, so I often use a ratchet strap to ratchet strap the kayak to the roof of my car. Have you ever seen them? There are a handle of ratchet straps and it tightens the strap in the car. Well, this company, they made ratchets, but they wanted to be able to actually fit this onto the handle of a ratchet, put a lever in here, and be able to actually get more leverage onto the ratchet strap, right? This would be for large ratchets, for maybe, do you ever see loads of pallets in the back of a truck, and they would just ratchet them on, they don't want them to be able to move, so they want to be able to get them as tight as possible, right? But the company made a number of different ratchet handles, and they wanted to ensure that their product fitted all of them. So they created different grooves and different shapes, etc. So that no matter what one you fit this onto, it fitted onto all of them. So they prototyped it first, yeah? Tested it out into different ratchets, it fitted them all. So therefore they said, okay, now we can go ahead and develop the tooling to actually produce this out of metal. And this is the final product, right? So before they went and spent tens or hundreds of thousands developing all the tooling and, you know, they probably had to get a machine specifically made to hold this mold, melt metal, and then pour the metal into that mold, okay? So it's going to cost them hundreds of thousands. So they want to make sure that the part that they're making this machine for is right first. So you can see, even though this did probably cost them €1,000 to prototype, they have a hell of a lot of peace of mind to ensure it's right, it's going to work, before they go and spend a few $100,000 developing tooling to actually make it out of metal. You understand that concept? Okay, so that's the SLA process. This is also SLA, and these are two. So blow molding, have you done polymer processing yet? Yeah, so blow molding where the parison comes down through it, they seal the parison at the top and bottom, and then they blow air into it and it fills it out. So bottle making is the most common use of blow molding. And this is for the neck of the bottle. And you can see if you look here, look, this is half the neck of the bottle. This is the thread where the cap would screw on. Okay? Now the problem with this was SLA'd, right? And they just drilled two holes in here. What do you think the idea of the holes were? Sorry? No, these were used for mounting, right? So you're correct, there are holes used for mounting. Remember the video I showed you with the holes going through a mold? What were those holes used for? Cooling, exactly. So they wanted to pump fluid in here to keep it cold, to prevent warpage. Okay, because they'd be producing bottles in a few seconds, blow mold bottles, right? And the heat from the heated parison will transfer into this, and it'll keep getting very hot, very hot, very hot. And eventually you'd end up getting warped necks on the bottles. Alright? So if you look at these carefully, these are two straight holes, drilled straight in, and they weren't adequate. They didn't cool it enough. Okay? So the SLA process was used to make a curved hole. And the curved hole actually passes through more of the product. So it takes away, it dissipates a hell of a lot more heat. So it takes away heat and it increased productivity, etc. Right? They didn't have to wait, didn't have to keep the mold open to let it cool down at a certain temperature and close it. Because there was a constant flow of temperature flowing through more of the mold, because of a curved hole, which is otherwise impossible to make. You can't drill a hole like that. You can't get bendy drill bits. Alright, no such thing. Okay, so the SLA process was used for that. Another interesting component which was also produced using SLA is this part here. And this was produced using a nano composite. Right? What's a composite material? Sorry? Exactly, good man. It's like an alloy metal. You mix more than one and you get an alloy. If you mix more than one materials that aren't metals, we tend to call it a composite. Okay? So this is called a nanocomposite. What's nano? What's nanotechnology? Very small, exactly. So a micron is 10 to the minus 6 of a meter. Right? So minus 6. So if you took a meter, which is 1,000 millimeters, yeah, and went back 6 decimal places, you get 0.001 of a millimeter, 1,000th of a millimeter. Nanotechnology refers to 10 to the minus 9. So now we're going back 9 decimal places from a meter, so you have 10 to the minus 6 of a millimeter. So you're talking about 1/100,000th of a millimeter. So you take a millimeter, you divide it into 100,000 pieces, and that's the size that you're talking about when you're talking about nanotechnology. Okay? So these are nanocomposites. So they reckon that the carbon fiber particles that are put into the plastic are smaller than 10 to the minus 9 of a meter. So tiny, tiny particles of carbon fiber. Okay? But they're sitting in this vat of polymer fluid. Alright? So now, when they create it, that carbon fiber is actually embedded in the rapid prototype piece. Okay? And that creates like an unbelievable degree of stiffness. You've carbon fiber in here. Yeah? So Formula 1 racing cars, high-end mountain bikes, you know, crash helmets, all that sort of stuff is made out of carbon fiber. Unbelievably lightweight for the strength that you get, strength and stiffness that you get. Okay? And the other thing about this, because of the carbon fiber in it, it's actually able to withstand temperatures of up to 220 degrees Celsius. Right? Polymers usually won't be able to withstand. So the additive, yeah, polymer pros, you talk about additives. Yeah, so this is a composite additive, carbon fiber additive, right, in a dust format. Actually enables this to be unbelievably strong, unbelievably rigid, but also withstand very, very high temperatures. Okay, so now this is this was a part that had to go into an oven, and the oven was going to be operating at 150 degrees Celsius. Now we know that this prototype is able to actually go into that. Maybe it's going to be eventually a metal part, but we want to be able to prototype it first out of plastic. But now we know that we can go into the working environment that it's going to be used in and operate at up to 220 degrees Celsius. Okay, so it's almost endless what these engineers are able to do with these processes at this stage. That's the SLA process. Okay? Unfortunately, our SLA, they were all done here in the college, but it's over in our research hub over the far side of campus and locked away because it's such an expensive machine in case we need to spit into the vat or something. Okay, so that's SLA, stereolithography. This is SLS. What does SLS stand for? Yeah, so the second S is sintering. Selective laser sintering. Okay? What's sintering? Anyone any idea what sintering is? Sorry? Exactly. Melting resin molecules so that they actually flow into each other, they solidify and they become one part. Right? So resin is just very, very small pieces of the material. Right? So remember the bed on the sintering machine moved down, a layer of polymer resin was rolled across, yeah? So it's compacted, and then the laser sits selectively, right? So selective laser sintering. It selectively moves about and melts the next layer. Right? So just like that machine moves around and cuts a particular cross section, the laser would actually go and actually fill in all that space as well. So it would go around the outside of it, it would fill in all that space and solidify that cross section of the object. Do you understand that? Okay, so that's selective laser sintering, and you can see the intricate detail. Most of you have, some of you have even hit this with a hurt, but you can see the intricate detail of that object. Yeah. Okay? Not possible with other manufacturing processes. Yeah? You couldn't possibly achieve that with any other process. You wouldn't make that your engineering room for that. Alright, not possible. You'll also see it, I'm sure you've looked at these as well. Okay, it looks like a chess piece, but if you look carefully, there's actually a stairs internally in it. Did you see that? Pass that down along. Anyone that hasn't seen it, look inside and you'll see. And then this is the exact same part. What do you think about this? It's metal. Okay, so this was the direct metal laser sintering that I showed you the final video, okay? So imagine very fine metal dust, right, or molecules, right? They're exactly the same way. You start, you move down a layer, you put a layer of metal molecules on it, the laser melts them together, it moves down, brings another layer of metal, and it's melted on top of the next layer. And like the surface finish that's achieved. You can't see layers there. Do you know the surface finish and the detail that's achieved is unbelievable. So that's SLS, all right, selective laser sintering. Okay. What's the next one? You tell me and I'll show you. Almost. FDM. What does that stand for? Fused deposition manufacturing. Right? Okay, so fused deposition. Right, so think about it. It's fusing the layers together, right? And it's like an inkjet. It actually deposits a layer of material that's coming from a spool underneath the machine. So you're not talking about a vat of polymer liquid or a vat of polymer resin. Now you're talking about an actual spool of material that's being fed through a nozzle. Okay? Actually 2 nozzles. So you can imagine if we were building this hurl, and as I was saying in the lecture, I can see the layers of that running in this direction. So that was built like that for some reason. Imagine it would have just built like that. But obviously for strength possibly, they built it like this. Okay? Now when this was built, it would have started here. This would have been the bottom layer, right? So when you get to here, what happens is you need to start filling in this space so that you can build on something here. You can't just build on fresh air. Yeah? So you need to start building a support structure under this. So that's why we had 2 nozzles and 2 spools. One being the actual polymer to produce the product, and the other being the polymer to produce the support structure or the support lattice underneath the product. Okay? So that's FDM. Rubber products there, so I thought there was 2 FDM products. Yeah, here they are. So this is a concept model for a mouse. Okay, so someone was trying to develop a new mouse for a computer, okay? And you can just see, this is interesting to look at because you can see you actually get quite a poor finish from an FDM rapid prototype. Pass that around, you can see all the printed layers. So it takes some sort of chemical finishing and actually rub a chemical along it and it kind of melts the surface of the layers together, or else a sanding process where you actually get a fine sandpaper and sand it smooth and then finish it. But you can also see here that this is it when it hasn't been. This is the support structure. So this would have been printed in this orientation. And you can see the different material. So this is the actual product material, the white material, and this grey material is the support structure, which easily cracks away. See it here with the break off. Okay, so it's just peeled away. Alright? Don't forget, it's post-processing, and it's a part of rapid prototyping that's rarely spoken about by the people that are selling their machines. It takes a hell of a lot of time, and it's, you know, it usually has to be done. The only one that doesn't have to be done on is that guy there, and maybe these guys here as well, the sintering. Usually they can get a very high level of detail that doesn't need to be post-processed. Alright? Okay. And the final one that I spoke to you about then was LOM, which is, yes, laminated object manufacturing, right? You drag a layer of material in, you cut a cross section, etc. Right? And it's the only one that really has a waste material. You can see I'm breaking blocks off as every group comes in here. This is the waste material, right? The only thing that we don't mind about this waste material is what? It's paper, so it's incredibly cheap, and it's fully recyclable. And you think, no, is it recyclable or is there glue in between each layer, right? But the thing about, this is an Irish company, proudly enough, right? So we can be proud of this technology. It's an Irish company that uses a water-based glue, a water-based heat-activated glue. So all that paper is perfectly valid for recycling. Okay? Any questions? Good, because they can't talk anymore. Okay, I hope you get an insight into the, did I show you this? Did you see this? So this is what I was talking about, the fashion industry availing of rapid prototyping. Dylan had a good look at it. So one of our girls over in the research hub was heading off to the Galway races, didn't have a fancy hat for Ladies' Day, right? So designed her own hat using the 3D CAD process, converted it into an STL file, and then it's perfectly valid for rapid prototyping. So the rapid prototype, quite an expensive hat actually, when you think about it. Yeah? And it withstood a night out in the town to Galway races, so it's quite a formidable piece of plastic. You haven't been yet, obviously. So that's basically it. You can see there's other molds here. So this is a mold for producing, if you look closely, it looks like the strap of a watch. Okay, so this here is the bottom half of the mold. This is a cavity that we want in it. So we want to be able to fit pieces of electric kit into this area. So they actually fit this into the mold, right? That way, obviously. This is the top of the mold then, so it sits down on top of it. Should. Okay, so the short bit goes this side, and like that, and then this one goes like that. Okay, so that sits there. These are all bolted together, alright? And then a silicone material is injected down into this. Okay, so it fills the mold with a silicone material, like the material that your watch strap will be in, right? Some sort of a silicone material. Okay, and then what they do is, so you can take that out then, and the mold would have been filled apart from this void. Okay, and this was for some, for a wrist, not a watch, but a component that an electronic board would have been slid into that compartment then. Okay, and then, I actually think, can I just have that little seal again? That's actually the prototyped cap, right? So that sits down on top of it, and actually what that is then is, that's a prototype that would actually test the flexibility. So you can imagine what this is, some company that has a door that you only want certain people to be able to access. So they put a chip inside that wrist strap. This is a little button, see it? Okay, so they prototype this material to actually see, is it flexible enough to act like a button? Is it too flexible, is it too stiff, etc. Right? So then obviously they were able to walk up, press the button activated a button on the board that was inside this wristwatch, etc. And all that was developed and researched here in AIT. A company would have come up with the idea, they would have come to us, and then the prototyping would have been done here in AIT, using the SLA process. Okay, the last thing I have to show you before I completely bore you to tears, look at those 3 domes. Nice one. Okay, so the other thing that we do need to consider, and this I was trying to sit down and I was trying to think, okay, what could they ask these guys in a leaving sort of question that's going to be the A student, right? What are they going to ask the guy that's going to think about this and he's going to get his A? And it's really about build orientation, right? Don't take my word for this, but I'd imagine it would be something that they think about. And the build orientation of the object, so you can imagine we built the exact same product, but we orientated differently in the machine. So this one, we built it like that in that orientation. This one, we built it upside down, and this one we built it on its side, like that. Okay? Now if you look at the tree, this needs a support structure underneath. It always comes 8 or 10 millimeters away from the table with a support structure, just so you can get your hands in under it and take it off the table when it's finished. Right? But it also needed a hell of a lot of support structure inside, okay, to be able to hold the top surface when it was printed. Right? So that's that one. Now if you look at that, you can see the layers along the side. Okay, so there's a number of things being affected here. One is the amount of material that's being wasted to build support structures, and then the other is the quality of the surface finish when you actually get your end product. Right? So that's that one. It didn't end up being the best. This one was built in this orientation, right? And it's fine, there's good surface finish along here, but you get poor surface finish on this top. So when it becomes more horizontal, right, so the curvature becomes closer to being horizontal, we got a poor layered finish, like we saw on the camera. Yeah? And then finally we had this one. Okay, and this ended up being the best because you can see minimal amount of support structure required, right? Because most of it was in the vertical orientation. So I was actually able to start building this. You can see there's a little zigzag, tiny zigzag that goes in from this support structure into the middle, so it could actually start. But the real thing, the real advantage was the surface finish on this one. Right? It's a really smooth surface finish up here. Obviously, this had to be broken away, and when this was broken away, there would have been a ring left that needed some sanding, some finishing, some chemical finishing. And that's the end product as a result of this. If we pass them around and just look at the cross sections, look at the layered finish, and actually look at the final product. Now that final product has been post-processed. Right? So one of our research students took it and sanded it and processed it so that it feels like a proper product. So pass it as the finished product, we'll pass it that way. That's the one that we used, that's the one that we didn't use, and that's the one that we didn't use. Just have a look at the different ones. You're all going to ace question 1 part B, I hope. Is that? Actually brought down to you. I have a better model of a racing car that has a front and rear aerofoil. You could look into designing it. Maybe your aerofoil is designed. One of them has to be adjustable or something, doesn't it? Yeah. Did everyone see these? So you can imagine, like, that's the parts. I don't know what part C of the question is going to be, okay? But it's going to be something that's going to make you think, right? It's not going to be the one that will say, okay, list 3 different rapid prototype processes. And you're going to be able to say stereolithography, selective laser sintering, and fused deposition modeling, right? That's part A, 5 marks or something like that, okay? Then it'll ask you, okay, pick one of the processes above and draw a diagram and describe how the process works. And you're going to draw an SLA machine and describe how the platform moves down and how the, moves 0.1 of a mil, the laser comes and solidifies the next layer and the product is built layer by layer. Yeah? But then part C of the question is going to be one that's going to make you think for yourself. It's going to be the trickier part. It's going to be worth the final 15 marks out of, I can't remember what it is, out of 50 marks or whatever it is. Yeah? So rather than just getting 25 out of 50 marks or 35 out of 50 marks, it's the last bit that you'll actually be able to think about the process that will get you your A marks. Yeah? Okay.